Things are going all right? All right. Well, let's keep going on then with our discussion of properties of matrices. Finish that section up and then get into inverse matrices today. So we did some properties of matrix arithmetic last time. Talked about how addition behaves pretty much like you would expect addition to behave. It's commutative, it's associative. If you do scalar products, it distributes over addition. If you do matrix products, it distributes over addition as well. So addition's pretty well behaved with respect to matrix addition. Matrix multiplication is almost as well behaved. You have associativity of matrix multiplication, and I already mentioned about the distributivity. However, we've already seen an example of the fact that matrix multiplication is not commutative. The order does matter when you multiply matrices. Pretty much if you take two random matrices, even if you take two square matrices that have the same size and do the product in the either order, you're probably going to get a different answer. It's a pretty rare occurrence, if you will, to have matrix multiplication actually commute. Okay. So just to illustrate, I'll write down no just to make sure that I emphasize that. Just to illustrate, if I do, say, 2003 and multiply it by the matrix 1, 2, 3, 4, what do we get? Okay. Yeah, notice that 2 basically multiply the first row by 2, and that 3 multiply the second row by 3, right? This is where I place the zeros. If you do it the other way around, what do you get?
2, 6, 6.
Good. Notice that your diagonal stayed the same, but your off diagonal ended up changing numbers, right? So notice that you didn't get the same answer. Notice in this case, it basically had the effect of multiplying the columns by those individual numbers, right? The first column got multiplied by 2, the second column got multiplied by 3. Okay. So even when we refer to this as a diagonal matrix in particular, when we have it written like this. When we have a diagonal matrix, even a diagonal matrix won't necessarily commute. That has a different effect depending on which side. Now, I could make a diagonal matrix commute. Notice I said that this one had the effect of multiplying each row by that number, right? Multiply the first row by 2, the second row by 3. On the other side, it ended up multiplying it by, the columns by those numbers. If I wanted to make that diagonal matrix commute, what should I do with each of the numbers that weren't 0 there? What could I do to make it commute? Make them what? Sorry? Is it here said?
I said make them 0.
I could make them 0. That would work, absolutely, because it would kill everything, right? Make everything 0. That would work. What else could you do? Notice that this is multiplying by 2 different numbers. What could you do instead? Make them the same number, right? If I would have done 2 and 2 on my diagonal, it would have worked. Or 3 and 3 and so on. And we'll see why here in a little bit, why that would have worked. But generally speaking, matrix multiplication does not flip around. It may not even be, it may be defined one way and not defined the other. By the way, we have to define our matrix multiplication, right? So that's the big deal. Look at this next property here. It says if we have A times B equals A times C, does that always imply that B equals C? Well, you know that it does for real numbers as long as you don't multiply by 0, right? If my A is not 0, I could divide by it and get rid of it and cancel, correct? Okay. Does it work here? Well, let's do another example. Let's say I had the matrix 2, 3, 1, 1, and I'm going to multiply it by 1, 2, 0, 0. Oops, I should do it on the other way. On the other side. Sorry, let me write it on the other side. 1, 1, 0, 0, and multiply by 2, 3, 1, 1. And then do the same thing, but I'm going to multiply by 2, 3, 2, 2. What do you get when you multiply?
Four,
0, 0. I think I messed up when I did this. It's all right. I'll fix it. I need to change the other matrix here real quick. Sorry. Let's change this to flip it around. What do we get? Sorry, I just needed to flip my rows around. What do I get in this case?
one, right?
I get 3, 4, 0, 0 again, don't I? So here I've got, if this is my A and this is my B, and this is my A and this is my C, I got the same thing when I multiply, right? I got AB equals AC because B equals C in this case. No. Okay. So the answer to this is no again. We don't get this cancellation property. If we have AB equals AC, then we can apply B equals C as long as A is not 0. We call that cancellation, being able to cancel the A's. We don't get that, generally speaking, for matrices. We're going to talk about today when we do get a cancellation property. Okay. It needs to be a special condition on your matrix to be able to get that cancellation property. All right. So notice that there's two properties of multiplication that we see with real numbers that we don't see with matrix multiplication. Not commutative, and you don't necessarily get cancellation. I've got a non-zero matrix here that I've multiplied two other matrices by. I got the same answer, but the two matrices we started with weren't the same. So that's the big thing about this idea here with matrix multiplication, is that we don't get necessarily the properties that we've had before. All right. So I know this seems like we're switching gears a little bit, but now that we can actually talk about matrix multiplication, and we've already talked a little bit about how we can write a system of linear equations using a matrix equation, we can formalize what we've already noticed about the number of solutions of a system of linear equations. Inconsistent means we had 0 solutions. We've seen consistent with a unique solution. We've also seen consistent with infinitely many, right? And those are the only possibilities you can have for a linear system. Now that we've talked about matrix multiplication, let's see why. So again, the possibilities are no solution, one solution. The third possibility is infinitely many. And we're going to go through the proof of this, why this is true. Mainly because it's not that hard of a proof to do. But the other part is showing how we're going to get this infinitely many part as the other possibilities. Notice this, you can't have all three at the same time. So it's this or this or this. So to prove that this is your third and final case, we'll assume that we have more than one and get that it has to be infinitely many. Okay? Does that make sense? All right. So let's say we can write our linear system AX equals B. Suppose that this has two distinct solutions. Say x1, and x2. What does it mean to be a solution again? Just generally speaking, for any type of equation that you have, what does it mean to be a solution? Say it again? Is the answer to the equation. So what happens when you plug it in? It gets a true statement, right? When I plug the answer in, I get a true statement. That's what it means to be a solution. So in this case, if I plug in x1, I get b. If I plug in x2, I get b. Right? That's what it means to be a solution, right? You plug it in, it works. So I plug in x1, I get b. Plug in x2, I get b. Oops, I wrote b2. This should just be a b. All right, so what happens now if I subtract them? What am I going to get if I subtract the two of them? You get 0, right? I'll write 0 with a vector over it because I mean the vector with all zeros in it. Oops. Now we've learned some properties of matrix multiplication. What can I do here with respect to the multiplication? I've got a times x1 and I've got the same a times x2, right? What can I do? Yeah, pull out the a, right? We had the distributivity property worked, correct? When I pull out the a, am I going to pull it out on the left or am I going to pull it out on the right? That matters for matrix multiplication, right? It matters on which side. Which way am I going to pull it out, left or right? Left, good. Because it's on the left side of each piece, right? By the way, this is important as well. If this were a times x1 and this were x2 times a, I couldn't pull out the a. It's on the wrong side. They both have to be on the same side to pull it out. All right. Just to remind, as far as definitions go, when I have a system of linear equations and I have a 0 on the right-hand side, what kind of system do we have? What do we call that when there's a 0 on the right-hand side? Homogeneous system, right? Okay. Notice that x1 minus x2 here is a solution to the homogeneous system, right? If I just wrote ax equals 0, which would be the associated homogeneous system, I have a solution. Is this solution 0? Is this x1 minus 2 equal to 0? By what we're assuming. Is x1 minus x2 equal to 0? No. If x1 and x2 are distinct solutions, when I subtract them, I don't get 0, right? Okay. So I'm going to write down, notice that x1 minus x2 is not 0 since they are distinct. I missed. Oops. So now let's consider and spell any real number c let's multiply x1 minus x2 times c. As long as c is not 0, is that going to be 0? No. Okay. As long as c is not 0, that's not 0. Using one of our properties, another one of our properties of matrix arithmetic, what can you do with the c? Okay, I can distribute it, that's true, but I want to do something else with it. You're right, I can distribute it. What else can I do with it? I can pull it out in front, right? Doesn't matter where the constant goes, right? So I can take the c and move it out in the front. Oops. But what did we just say that this product right here that I'm underlining was equal to? 0. And C times the 0 matrix is going to be 0. Yeah. So what did we just create? Let's go back. We said that this was a solution to the homogeneous system, right? It's a non-zero homogeneous system. So what did we just create by multiplying that solution by a constant? A whole bunch of solutions, right? I just created infinitely many solutions to the homogeneous system, didn't I? We have a solution to the homogeneous system for any constant. So I just created infinitely many solutions, right? Okay. Now let's go back to the original system. If I take A and plug in, multiply it by, say, x2, we'll use x2 in this case, the way I've got that subtracted. Once again, we can distribute the A through. We said x2 was a solution to the original system, so what's this part equal to that I just underlined? B, good. What's this part equal to? 0. And B plus 0 will give me B. So what did we just do? You just told me there's infinitely many vectors that look like this, right? So what did we just create? All of these are now a solution to the original system. So how many solutions do we have? Infinitely many, yeah. Since x2 plus cx1 minus x2 represents infinitely many solutions, or infinitely many vectors, I should say, we have ax equals b has infinitely many solutions. Now, for those of you who have had differential equations, and I know some of you have, you've solved non-homogeneous differential equations. How did you do it? You found the homogeneous solution, and then you found a particular solution that worked, and then added them together to get all possible solutions. And if you're currently in differential equations, you'll do that exact process that I mentioned, and that's how you know you're getting all of them. And that's why you only need to find one particular solution, right? Because from the one particular solution, I can create the rest of them by looking at the associated homogeneous system. All right. In any event, that actually proves what we were talking about before. If you have a linear system, there's only 3 possibilities. No solution, which we call inconsistent. A unique solution, which is consistent but a unique solution. Sometimes that's called independent. Or infinitely many solutions, which we call dependent. Those are the only possibilities. Questions on that at all? Notice we waited until we could actually talk about matrix multiplication and run our our systems this way so we could talk about the solutions a little bit more easily. All right. We're going to go on to inverses today. Before we do inverses, we need what we refer to as the multiplicative identity. Again, since the way matrix multiplication is defined, we need an identity matrix for every size that we could multiply by. Okay. So when we do this identity matrix, it's an n by n matrix. It needs to be square. Okay. And the way we form the identity matrix, I'll write it rectangular first. We'll put a 1 in the upper left-hand corner and then zeros to fill out the row. Second row, we'll put a 1 in the second column. And keep going down your diagonal. Oops. Actually, go down the diagonal. All right. So you get this diagonal matrix with 1s down the diagonal and 0s everywhere else. Another way you might have defined this would be to just talk about the individual entries. And this is why I said I was going to save the E for the special case. It's a J. The diagonal entries are where your subscripts are the same. So I can define it as the general entry is 1 if the subscripts are the same and it's 0 otherwise. Why do we get this as our identity matrix? Well, if I want the identity matrix, remember we want to make sure that when we multiply our matrix through our identity, we don't want to change when we multiply, right? We want when we multiply, I want to get the same thing that I started with, right? That's what multiplying by the identity means, right? It doesn't change what we multiplied or multiplying. Why am I using an M and an N here? Why do I have different letters? This works even if A is not square. So if A is M by N, I need to make sure my columns here match right. That's why I have an M here. And I need to make sure my rows here match right. Okay, so that's why I've got different letters. I really did mean the different subscripts there, yeah. So you may even have to change the size of the identity matrix depending on what you're multiplying by. But this is what it means to be an identity matrix. So let's see why we want to define it this way. Remember when you multiply on the left, I match my row with my column. Well, notice in my first row, when I go across my first row, I'll have this 1 hit the entire first row and 0s will hit everything else. So the only thing that gets saved is the first row. Second row, same thing, right? I've got that in the second spot. Remember not a minute ago, it's been longer than a minute. When I did that example of that diagonal matrix, it said when I multiplied on the left, that 2 got multiplied by the first row and the 3 got multiplied by the second row. Here I've got 1s, so that when I'm multiplying by 1s, I'm not changing the row. Right? We also said if we would have used the same number down the diagonal, it would have done the same thing to the whole matrix, right? Even though we did row versus column, and now I'm just multiplying by 1s. If I put it on the right side, I multiply the first column by 1, or I multiply the second column by 1, or multiply the third column by 1, and it doesn't change anything. That's why we use 1s everywhere. So this is what our identity matrix looks like. I've already mentioned part of the properties that we have here. So, pardon me. I'll write them down here where I've got them listed out separately. So, again, let's suppose we have A is an M by N matrix. Then, if I multiply on the left by IM, I get A. And if we multiply on the right by IN, I get A. All right. Now, why do we care about identity matrices? Good question. Remember, the reason why we care about identity in general is because, for example, if you wanted to solve the equation 3x equals 9, what do you do to solve that equation? Divide by 3, right? Or multiply by the inverse. So you can think about it as multiplying by a third, right? Why do we do that? Because, well, I'm going to go through it longhand here. First, I have to reassociate. And then when you multiply these two things together, what do you get? 1. And the reason why you want 1 is because 1 times anything is itself, right? So in terms of matrices, we want to do something similar. The whole reason when you're doing equation solving is I want to get that to be the identity. If I want to undo multiplication by a matrix, it's not getting to 1, it's getting to the identity matrix. Okay. This is why we care about identity matrices. It's going to be when we start doing inverses here later today. Okay. All right. But before we do that, let's talk about one more operation that you do with a matrix. This operation is referred to as generally speaking, this is called a unary operation, which just means it's an operation applied to a single matrix. Addition and multiplication are binary operations because it takes two matrices to combine. Okay? So unary operation means you only take one matrix and do something to it. Binary operation is you take two matrices and put them together. So just learn a new word today, if you will. Okay. All right. So how do we define the transpose of a matrix? Well, let me just do an example first, and then I'll go write the actual definition. Okay. So let's say we start with the matrix 1, 3, -1, 0, 2, 5. Okay. Say we start there. And I want to transpose it. Well, what transposing does visually is you do a reflection about that diagonal. Start in the upper left-hand corner and make a diagonal go down. And visually, you reflect it. So think about when you did inverse functions back in algebra class, where you would flip across the line y equals x, and so horizontal lines become vertical lines, and vice versa. So when you do this reflection, that horizontal row will become a vertical column. So rows become columns, and columns become rows. Okay? So when we do the transpose, which we denote with, it looks like an exponent, it is not an exponent. It's just our notation for it. Okay? When we do the transpose, we'll take the first row and make it the first column instead. So it's like horizontal lines become vertical lines. Does that make sense what I'm saying from when you did inverse stuff before? Same idea here. The second row becomes the second column. Okay? So that's how we make the transpose. So when we do the transpose of A, what we mean is it's an n by n matrix, n by m matrix, where the rows of A transpose are the columns of the original, and vice versa. So since we're flipping rows and columns, it also flips your dimensions around. So if you start with a 2 by 3, you end with a 3 by 2, which is what we see over there. If we were to write this in terms of general matrices, so if I write this in terms of, I should say general matrices, I mean general entries. If A is described by A sub little ij, then A transpose, where I'll call B sub little ij, that's going to be an n by m And then I can write down each of the general entries. B sub ij is just A sub ji. It flips the entries around. Basic, yes. Mm-hmm. Yep, you can do a transpose of the square matrix as well. It's the same thing. Just you get the same dimension. The dimension won't change in that case, but you still just take your rows and make them columns. So if I do a square matrix, if I say I have 1, 7, negative 2, 5, 0, 6, 2, 3, 4, and I want to do its transpose, what would I get down the first column? 1, 7, negative 2. Second column will be 0, 6, and the third column will be 2, 3, 4. Yep, you can do it the exact same way. As far as operations go, it's one of the more straightforward ones, right? I can look at the matrix and just go row by row and just write it column by column. All right. Transposes behave nicely with respect to some operations, and then it does something that seems a little strange in the last part. So this one hopefully makes sense. If I transpose a matrix and then transpose it again, what do you think we end up with? Yeah, the same thing, right? If I make rows into columns and then back into rows, I get back to where I started. Okay. And it kind of is like that reflective property, if you will, right? If I change a horizontal line to a vertical and then change it back to horizontal line, I'm back to where I started. If I add two matrices together and then transpose them, I might as well have just transposed them first and then added. This works because of the way that we add, right? We just add entry-wise, right? So I can either add across the rows first and then flip the row into a column, or flip the rows into columns first and add them together. They're still in the same relative spots, so it doesn't change anything. Third one might be even easier. If I take a constant and multiply it by a matrix, well, that constant gets multiplied by everything, right? That constant goes to every single entry, doesn't it? Does it matter if you do that first and then take the transpose, or flip it around and then multiply it? No, it still gets multiplied by everything, right? So this is the same thing as the constant times A transpose. All right. The last one is a little tricky, but let's think about it. Let's say if A is, say, a 2 by 3 and B is a 3 by 4. Let's start with that. Can I multiply A and B together? Yeah. Can I multiply B times A? No. Okay. So AB is defined, BA is not, right? What will be the dimensions of A transpose and B transpose? What's A transpose's dimensions? 3 by 2, and B transpose is 4 by 3. Okay. We said that AB was defined, but BA wasn't, right? So I could do A first and then B. Can I do A transpose and multiply by B transpose? No. But it's the other way around, isn't it? I can do B transpose times A transpose. Yeah, okay. So this is why this is at least a little bit of an illustration of why the next property is what it is. If I do the transpose of a product, it does kind of distribute, but it flips the order. This is going to be B transpose times A transpose. Again, it can't be A transpose, B transpose in general because our dimensions may not match up, right? Another way to think about it is, again, remember we flip rows and columns, and when we multiply, we take the row of the first and the column of the second, right? If you want to think about after you flipped it, I probably want to do it the other way, because what do we do? A times the B goes this way, right? A times the B goes that way, right? But when we flip, the B becomes the row, and the A will become the column, and it'll still match it that way. So I need to put the B first to get the row to match with the column appropriately. Okay. That was the trickier property. We do use these properties later on. Transposes are important. I'm not sure we'll see a lot of the applications. I'm hoping we do. It pops up in doing least squares stuff when you're trying to do approximations of things. So if you've done any statistics at all, you've probably done a regression line or a least squares line. There's linear algebra applications of that, not only the lines, but doing some other types of operations, and the transpose comes up in those computations. So that's where that'll pop up. I'm hoping we'll get to it. Like I've mentioned at the beginning of the semester, there is so many applications to linear algebra, we can't possibly get to them all. So, in any event, any questions about how to take a transpose? Start there. Hopefully it's pretty straightforward, right? Okay. All right. So let's switch. Not really switch gears, but continue our discussion while we talked about the inverse or the identity matrix, so that we can talk about undoing matrix multiplication and come up with a process for doing that. So section 2.3 introduces us into the world of inverse matrices. Switch pages here. All right. So there's a couple of words that we use interchangeably with the word invertible, or with the word having an inverse. So A has an inverse. We'll say A is invertible is one of the words, or A is non-singular. That's another word that is used. So the definition, notice first that in order to do an inverse of a matrix, we need a square matrix to start with. Okay. The reason for that is because we want to get back to the same identity matrix, the same I sub n, namely. Okay. So if we have an inverse, we have another matrix. I'll call it B to start with, so that if I take A times B, I get the n by n identity matrix, and if I take B times A, I get the n by n identity matrix. Notice I want the same matrix to work on both sides. In order to get the same matrix to work on both sides, I have to start with a square matrix, because one of the products may be defined and the other one wouldn't be, right? So if I want the same matrix to work on both sides, I need square. That's why we have square to start with. Okay? So let's illustrate what we mean by this. Let's take these two matrices and multiply them in either order. Right? It says it has to work on both sides. So if we take 8, 3, 5, 2, and multiply it by 2, -3, -5, 8, what do we get? You can probably guess what we're going to get, or this would be the worst example that I could have possibly put on here to start with. It better be 1001, right? Otherwise, it'd be a terrible example, right? Okay. You can check the arithmetic, right? 8 times 2 is 16. 3 times -5 is 15, or -15, add. -24 plus 24, and so on down the line. Put it on the other side, you get the same thing. Again, a better, or It's a really bad example, right? But you can check the arithmetic that we really do get 1, 0, 0, 1. Okay. So these two matrices are inverses of each other. Oops, inverses of each other. Yes. Hmm?
Every time we come prove them and get a
If you flip them and you get the identity in both cases, it makes them inverses. You have to get the identity matrix. Yeah, it specifically has to be the identity matrix 1, 0, 0, 1, or one's down the diagonal and zeros everywhere else. It's possible that I could have two matrices and flip them around and get the same answer, but they wouldn't be inverses of each other. To be inverse, it specifically has to be the identity matrix when we're done. Specifically has to be that specific matrix. All right. Now notice that when I made the definition before, I said there exists an n by n matrix B, right? I said there was at least one. Now, you know from work that you've done with numbers, there's only one multiplicative inverse of any number, right? Before we said, how did I undo multiplication by 3? Multiplied by a third. You divided by 3, right? There was only one inverse. Now, the reason why we use the definition and say an inverse rather than the inverse is because in math, you don't like to assume things that you can prove. If you start assuming too many things, you can start introducing contradictions, and if you start proving things that are true and false at the same time, that causes issues. So we never want to assume more than we need to. We always want to try to prove it. And showing that there is one and only one inverse is something that we can show. Okay? So here's how that works. So let's suppose B and C are inverses of A. That, by the way, another reason why I'm doing this, part of linear algebra is doing an introduction to proof techniques. This is a very, very, very common way to show that something is unique in math. Assume you have two and show they're equal. Pretty much the default. If you want to show something is unique, show that assume there are two and show that they really are the same. Okay? So I'm assuming I have two, B and C, right? By our definition of inverses, we know lots of different products, right? What's A times B equal to? If they're inverses, what is it equal to? The identity. And if we understand what the dimensions are, then we don't bother putting the sub in every time. We'll just put an I, just because we're lazy. Mathematicians are inherently lazy. So if I don't want to write it, I'm not gonna. All right. What's B times A? I. What's C times A? I. And what's A times C? I. Good. Those are all I, right? Okay, so I just told you that I want to get to the point where we can say that B is equal to C. So I'm going to start a string. I'm going to start with B, and I'm going to do some steps until I see C. Okay? All right. There's not a lot we can do because we don't have a lot of information, right? In particular, I'm just starting with the letter B here, right? But what can I multiply this thing by and not change it? The identity, right? I can always multiply by the identity, right? So the first thing I'll do is I'll write B times I. That'll be the first thing. I haven't changed anything, right? You do this all the time, by the way. You insert 1. Tell me an operation where you insert 1 cleverly all the time when you add or subtract. There's certain things that you add or subtract where you insert one cleverly when you have to add and put them together. How about fractions? You insert one all the time, don't you? If I take 1/2 and a third, I have to get a common denominator, so you insert one cleverly, right? Clever insertion of 1 with the 1/2 would be 3/3. With the 1/3 would be 2/2, right? You do this all the time. You insert the identity all the time, right? That's all we're doing here. Same concept. Now, why did we do it? Do you see something that is equal to I and involves C? Actually, I see two things, right? I see these two things. Now, I got to be careful of which one I want to plug in because I can't flip the order necessarily. I can in this case, but notice that, do I know anything about B times C? No, but I do know something about B times A, right? So I'm going to replace the I with AC. Now notice my parentheses are around the AC. Can I move those parentheses? Yeah, we know matrix multiplication is associative, right? So I can take the parentheses and put it around the BA. And now what's BA equal to? I. And now I filled in the steps. I times C will be C. All right. So inverses are unique. So since they're unique, we can use a special symbol to denote the inverse. So we denote the inverse now, not an inverse, but the inverse. There's only one. The inverse of A by A inverse, the -1 up there. Be careful. This does not necessarily mean an exponent. What I mean by that is usually when you see something to a -1 power, you write that as a reciprocal. There is no such thing as matrix division. Do not write 1 over A. If you do that, you're going to see a lot of red ink. Okay? Okay? We don't do matrix division, all right? This is the symbol for the inverse of the matrix. Okay? All right. So, part of what we're going to do is come up with an algorithm to solve for any inverse of a matrix if it exists. Not every matrix has an inverse. But in the 2x2 case, there's a pretty easy way to do it. And we just do this by looking up above when we did the example. Do you notice something about the entries that we have in those two matrices, the way I had them written? Do you see something similar about one versus the other? Yeah, so notice I swapped these two, right? And we negated the other two, didn't we? Let's see what happens if we have that in general. Let's say I have A, B, C, D. I swap the ones that are on the main diagonal and then negate the ones that are on the off diagonal. What do you get when you multiply those two things together? What do you get in the first entry? You get AD minus BC in that upper left. What do you get in the upper right? Yeah. We get 0 in the upper right, don't we? What do you get in the lower left? Yeah, I get another 0, don't I? Because I get CD minus CD. And what do you get in the lower right? Yeah, I get AD minus BC again, don't I? So notice that if we simplify, I've got AD minus BC, 0, 0, AD minus BC. If these are going to be inverses of each other, what do you want this diagonal to be instead? A 1. Can you multiply it by a number on the outside and change those into ones? You can do 1 over AD minus BC, right? Provided that's not 0, correct? So that's actually our formula. The formula for A inverse is you do 1 over AD minus BC, and then do what we just did to start this problem. You flip your main diagonal, and you negate your off diagonal. That's literally the formula. And again, provided what happens? What can't we divide by? 0. So we need to make sure that our AD minus BC is not 0. So that's our formula for finding an inverse for a 2 by 2. Okay. Well, we will have an algorithm that will allow us to solve for, or find inverses for any size matrix we would like. But for, pardon me, for 2 by 2s, sometimes this is a little bit faster, right? Because it's a pretty easy formula to remember. Right. So we'll do more of these next time. Have a good weekend. I think you have homework due on Monday as well, so don't forget about that. Otherwise, have a good weekend, everybody. Enjoy the Super Bowl.